Section 9.4, real numbers. Now, any number that you can think of is a real number. But we'll talk about some that aren't real numbers, just as kind of like a side little note. But first, let's tackle the real ones. So, real numbers fall into two categories those are the rational numbers and the irrational numbers. Now, rational in definition is something like that's a very rational thought. It means it's something very logical. It makes sense. It has backing behind it. It's understandable. Irrational is kind of like craziness. It's kind of like crazy behavior. Like if you're acting irrationally, then that means you're kind of like all over the place. Your actions don't really match how the situation. You're kind of like let's say somebody is walking down the street and their gum falls out of their mouth just randomly. I'm sure it's happened to all of us. And instead of being like, "Oh man, rats," and getting another piece of gum, they might like flip out and go crazy and da 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 da. Like that's very irrational. It's not necessary, it doesn't make sense. It's kind of crazy and all of that. You can kind of keep those same notions when you think of numbers. So rational numbers are numbers that fall into certain concepts. Maybe they end, okay? In other words, they terminate, meaning a number such as like 3 or 4.12. It stops. It's kind of neat, orderly, nice, concise. It has an end to it. Okay, that's one kind of rational number. Another kind of rational number is something that does repeat, but that's exactly it. It repeats. It might be like 4.4 repeating, or 3.73 repeating, or zero point 0.1 repeating. Or zero point 0.12 repeating, or whatever the case may be. There is some pattern to it, okay? Or 0.8, 3, 3, 3, 3, 3, 3, 3, where the threes repeat. Anything like that, there is a pattern. Even though it goes on forever, there's logic behind it. It's not crazy. It has some kind of order to it, some kind of consistency, and it makes sense. The flip side of things are irrational numbers. These are numbers that never stop, and also with that, they go hand in hand, never repeat. Okay, so they're numbers that never stop or repeat. They have to be both of these. Okay, never stop or repeat. So a common irrational number is the number pi. 3.14159 da 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 da. It never stops, but nor does it repeat. It goes on and on and on forever. No pattern whatsoever to it. It's a rather crazy number, if you could call it that. It doesn't follow like a nice pattern. It just does its own thing. It's very irrational, very illogical, something like that. Rational numbers, again, they're the ones that stop. So there's some categories. Rational numbers, a branch of rational numbers, something within all the rationals are the integers. These are all the negatives and all the positives. So these are all rational numbers. They all stop. Within that, we have the whole numbers, which we study, like 0, 1, 2, 3, and so on. All of those stop. And then we also have outside in this area here all of like the decimals that go beyond whole numbers and integers, which might be like 3.17 or 4.2 or 5.9 or whatever the case may be. The negatives as well, negative 10.4. So our big area of rational numbers also includes the integers, the integers also include the whole numbers. That's why they're kind of inset the way they are. All of these stop, or excuse me, if they don't stop, they repeat a nice pattern. Irrational numbers, like we said, are rather illogical. Pi is a very common one. Other very common ones are square roots that are not perfect squares. Perfect squares we've been studying, those are ones like the square root of 16 is 4. It comes out to be a nice whole number. It falls in this category. The square root of 17, not so nice. Okay, so the square root of 17 goes on and on and on forever. It is not going to come to a nice whole number. Instead, it just goes like crazy. It goes on forever and ever. So that's an irrational number. Okay? So, irrational numbers, you can kind of just reference this. The real numbers is the collection of both collection of both rational numbers and irrational numbers. Rational and irrational. So it falls under both of these categories. Now, one side thing that I'd like to tell you, real numbers holds both of these. You might say, well, what else is there if it's not any of those, there's nothing else left, and that's true. Any number you can think of falls in that category. However, there are other numbers that are not real numbers, and those are known as imaginary numbers. And yes, there are infinite number of numbers in the world, but there's also more than that, imaginary ones, the ones that don't even really exist. They're imaginary. A quick little blurb about what they are. Square root of negative 49. We talked about how that's not possible. There are no two numbers you can multiply by themselves that are going to give you, that are the same thing, that are going to give you 49. 7 times 7, positive 49. Negative 7 times negative 7, positive 49. The only way is if one was positive, one was negative. So somewhere along the line, they realize that they keep hitting this wall when they get to negative square roots of negative numbers. Square root of negative number, you can't go past that. And I mean, there's a ton of different mathematicians that have worked with this, but they came to the concept that the square root of negative 49 can be solved, and this is how it's solved. On the imaginary plane, on imaginary coordinate plane, okay? So where this is imaginary. And by that I don't mean it's like they're envisioning things that aren't really there, but I mean they call it imaginary. What they do is they break it up using that rule we just learned where you can break up product of properties of square roots. I can say, well, negative 49 is really the same as 49 times negative 1, giving each their own little house. Square root of 49 is just 7. Then the square root of negative 1, that's not possible to have a negative under the square root, but they call it the square root of negative 1 is I for imaginary. So then they start graphing things, complex numbers, which you'll end up studying later before you graduate. So it is coming down the road. But I wanted you to be aware that there are these things called imaginary numbers. And actually they're a key component to this rather recent, when you think of the whole history of math, branch of math known as chaos theory, which studies like weather patterns and some medical issues like heart patterns. And it studies the kind of chaos stuff that actually has some verification using these imaginary numbers. And if you've seen Jurassic Park, the guy who's wearing all black, his name's Malcolm. He's like the cool guy, comes in like the black leather jacket and everything. He is a chaos theorist. He is a mathematician. And he says this right in the movie. He said, oh, I'm a mathematician. I study chaos theory. And that's when he drops like the drop of water on her hand when they're in the car, and they analyze that. It may have just gone by without you even catching it, but next time you watch it, pay attention. He says chaos theory, and this is what he's referencing. So it's kind of neat to see that stuff in real life being mentioned. All right, so with this though, even though I just took about a couple minutes to talk about imaginary numbers, we are only focusing on the real ones. So we're all good. What this lesson is going to be kind of asking you to do is determine whether a number is rational or irrational. Rational stops or repeats, terminates or repeats. Irrational goes on forever without repeating. So in example 1 says classify the following real numbers. We want to classify this number as whether it's rational or irrational. So the first thing I'm going to do is write it as a decimal. The decimal 5/8 is really 0.625. 0.625 is a terminating decimal, meaning that it stops. And so this is a rational number. Any number that stops is rational. Then I go ahead and I do 5/6. 5 divided by 6 is equal to 0.83 repeating. 0.83 repeating, that is a repeating decimal. But repeatings are also rational. They have some nice pattern to them. It makes sense. This stops. This goes on forever and ever, but it has a nice pattern. It's just the rest of them are just threes. Very logical, rational. Okay? Last one, square root of 19. Let me pull up my square roots. Square root of 19, now it's not a perfect square, so we know it's not going to stop nicely. It ends up actually going on forever. It's 4.35889894354 3588989. I won't keep writing them out, but obviously there's no pattern to this. Then the 8s and 9s do repeat, but not in any logical form. And actually, if I do write it out a few more, we see that then we have all new numbers introduced. So this is a not ending, not repeating decimal, making it irrational. Okay?